Hello. Hi. So I think let's just begin. My name is Oliver. I'm head of engineering at a company called Monzo. How many people have actually heard of it? I'm imagining not very many. Yeah, we're a bank in the UK. We're not just any bank. We're trying to build the best bank account in the world. We've been at this about 2 years now. We're a mobile-only bank though, so we don't have any branches. We've been live for about 18 months in the UK with prepaid cards, so not as a full bank. We have about 200,000 users on this, up from 100,000 about 3 months ago, so we're growing really fast, but currently it's only in the UK only. And we have all the kind of, just to tell you a bit more about what we are, we have all the kind of features you wish your bank had, basically. We try and give you kind of a clear, easy to understand transaction feed so you can actually see where you spent your money. I don't know how bank apps work here, but if you have a bank app in the UK, it's actually extremely difficult to even tell half the time where you've spent your money because you have these kind of 12 to 18 character, all caps statement descriptors that often don't even contain the name of the merchant or as you would understand it. We let you make straightforward and instant transfers to your friends through the app. So we kind of, pull in your contacts into the app and you can pay people immediately. We give you insights into your spending and help you budget. So if you have kind of a goal in mind or don't want to spend more than a certain amount every month, we'll help you do that. And we don't have any fees to use your card abroad. So while I'm here in particular, that's been really useful. You can just use your card as you would at home, which again is not kind of a standard feature of a bank account. You're used to paying a fee on every transaction or paying some spread on the interchange, which is some spread on the FX rate, which is not great for you as a customer. We also send instant push notifications with every transaction. So every time you spend some money, you get a notification telling you where you spent, what you spent, and you get an emoji with it, which people really love. We have a surprising amount of code dedicated in our backend to serving emojis. As I said, at the minute we're a prepaid card. We have about 200,000 of those in issue, but we were granted a full banking license in the UK a few months ago. So within the next few months, we will launch a full current account, as it's known in the UK. It's a checking account here, and it'll have all the kind of features you would expect. Bank-to-bank transfers, overdrafts will be a feature of that, kind of things we can't offer at the moment without that license. And all our users will have a full account by the end of the year. As I mentioned, at the minute, it's only in the UK, but one day, it's our ambition to be all over the world. Our technology, we're trying to build technology that's different to kind of what most banks would have. They generally would be the first to admit that they have kind of decades of legacy in their systems that hold them back. We are kind of building a core banking system ourselves from scratch using things like CoreOS and Kubernetes, so quite different to what you'd find at most banks. And my talk today is a little bit about some of the tools we're using or which we've built which kind of concern infrastructure security, and a little bit of sort of backstory about how we got there and how things evolved. In general, these are kind of general purpose tools. Kind of full disclosure, not all of these are fully built or live yet, but they are all kind of on the critical path to launching full accounts to our users. There's kind of 5 things I want to talk about at kind of a high level today. Some of these you'll probably know about already, and some of them are kind of things we've built ourselves. So yeah, please ask questions at the end. I hope this is useful. The first one is actually our architecture itself. So we have a microservices architecture, as everybody does. I'm sure I don't need to tell you all the benefits of that. We have about 200 of those currently. Well, we have about 230, I think, currently. And they all run in Kubernetes. There are some benefits to this from a security perspective as well, though. Everything is quite compartmentalized. It's very easy to kind of review and audit our services, or at least it's easier than it might be if it was all just one giant code base. And everything has a well-defined interface, so it's easy to see what data enters and leaves a service. So that kind of covers the first one. I'm not going to go too deeply into that. But from a network perspective, all these services need to communicate with each other a lot. And what this means is you basically have, in our case, literally thousands of dynamic endpoints in the network. So this is IP addresses who don't really mean anything on their own because they could correspond to something today and something else completely different tomorrow. And we found that a lot of traditional security tools aren't really built to cope with this. your typical or traditional boundary might be the host or a subnet, and that doesn't really mean a great deal when you basically just have this big soup of endpoints that can mean different things from one day to the next. And kind of a lot of the tools you might use traditionally, or the ones that like a cloud provider might give you, are kind of blunt instruments. Like, what do I put as my firewall rule, into my ACLs in EC2? Like, that doesn't work quite right. Kubernetes has an answer to this. It's called network policy, and it sort of defines what endpoints can receive traffic from other endpoints. And it's actually a lot more powerful than a traditional security boundary might be. You can basically place boundaries wherever we want, and that kind of extends the label selector concept in Kubernetes. But they are just an interface. This just allows you to specify what should be able to talk to me as a pod, but it doesn't actually implement it. Unless you have something that supports that, it doesn't do anything. So in our case, we use Calico to provide that. We don't use Calico as a network, but we do use it to enforce policies. And as I mentioned, there are some pros and some cons to this. The good thing is it does kind of live in this world where endpoints are very dynamic, and it will adapt to that. It uses IP tables under the hood, which we think of as a very good thing as well. That's a very well understood technology that's been deployed for years, decades even. And one of the other good properties of it is the network filtering happens kind of at both ends. Rather than at this one point in the middle where stuff gets filtered, it gets filtered at egress on one node and at ingress on another node. But there are some limitations of this. One thing is that in the kind of current network policy implementation in Kubernetes, it only controls ingress into a pod. It does not control egress from a pod. So while the traffic might be filtered according to the ingress policy of the destination, it isn't filtered according to an egress policy of the source. And this is quite important for us. Most of our services, for instance, have no business accessing the internet, and if they did, that would be a fairly serious problem, and something's gone quite wrong there. So this is one way we've had to extend it. Calico does support egress filtering, and it does support the next thing as well, which I was going to come on to, which is that network policies in Kubernetes only deal with TCP and UDP traffic, but other things are quite important for us as well. Like, not all of our traffic on our network are those things, and there are other things you would want to filter even if your communication is both those things, like ICMP, for instance. So we've actually built a service that kind of synchronizes between Calico's more rich network policy, which can filter those things, and some definitions we put in third-party API objects in Kubernetes. And at some point, I think it would be nice to kind of extend the network policy to support these things, but that currently is not a thing in Kubernetes. Also, for all our RPC traffic, I'm not going to talk about how that works in this talk a great deal, but proxies are involved. So this kind of, in a naive implementation, would break the network isolation, basically. Because if your proxy has to be able to access all the services, and you're able to access the proxy, that doesn't, that kind of breaks your isolation. So we have had to write a plugin for our proxy to kind of make it understand that. That kind of gives sort of a quick overview of how we secure one aspect of the network within our cloud environment, but we have a lot of interesting requirements to connect to a lot of third parties. And a lot of these are payment networks, and often payment networks do not run over the internet. They want to bring kind of a physical line to you. And we have kind of tens of these right now, approaching tens of them right now. And we're likely to have hundreds in the next few years, I would imagine, as we expand internationally. So this kind of gave us the dilemma of how do we connect these two things together? We can't really just take a wire from these payment providers and plug it into the cloud and say to AWS, can you just plug this in? It doesn't really work like that. So we realized we would need to add kind of physical infrastructure to our platform. So we kind of added some co-location facilities, and this is my colleague Matt in one of them. So this kind of solved the issue of how to connect these third parties to us, but it did not solve the issue of how to connect our cloud environment to our data centers. And we kind of thought this would be a simple problem and kind of a very easy to solve one. And it was one we were going to have anyway, I suppose, when we went to kind of a multi-region setup, but it isn't something we'd tackled then. So what we tried initially was kind of a very traditional approach, I suppose. We bought some hardware appliances to put in our physical co-location facilities, which would, in our minds, terminate a VPN connection. But we quickly got very frustrated with this approach and didn't find it worked very well in our setup. And kind of one of the reasons is because of what I mentioned earlier about how network endpoints are very dynamic. And that doesn't really work with a lot of this hardware. You know, if your kind of one end of the VPN can be running anywhere in this cloud infrastructure, like they don't really like that, and they're not built for that. And also another problem we found was there were large kind of implementation inconsistencies between what you'd find in these hardware appliances and what you might find in the open source version, the Linux implementation. And we basically got incredibly frustrated with this, and it was a poor fit for our team's skills, and I think any kind of software team skills. So we kind of got rid of that and went down a slightly different route. What we decided to do was basically put in Linux servers in these data centers. And instead of using IPsec, we used kind of a newer VPN called WireGuard, which we found was a much better fit with kind of a container infrastructure. It did have the downside that we spent a lot of time kind of learning about much lower level Linux stuff, for lack of a better description, like networking and tunneling, and kind of there were lots of other things as well. Like we didn't want these things to be single points of failure, you know. So then we have to learn about how to do kind of active-passive pairing with Linux servers. Or another thing was about how do we even get these things running in the first place. You kind of want to build images for these things and be able to manage them as you might any other software in our cloud environment, but that doesn't come for free. But in learning all of those things, we kind of ended up with, in my opinion, a much better solution, and one that required a lot more skills than we already have, but those skills are kind of directly applicable to our cloud environment as well. You know, we learned a lot about our own system in the process, I would say. The next system I wanted to move on to is about secret management. This is kind of more in the application layer, but still something we consider to be like a platform service. We find that like any company of a sufficient scale ends up with tons of secrets. And secrets for us are things like encryption and signing keys, certificates, API tokens, in some cases passwords, depending on kind of the third party you're talking to or using these with. And often these things are managed in quite an ad hoc way, and they become very difficult to manage, especially if you have something like a security team who wants to be able to manage these things, but they're spread around everywhere, basically. These things do have a lot of common requirements, though. Like, we would like them to be encrypted at rest, so we don't really want these credentials in the clear somewhere. We would like the access to these credentials to be authorized, so most of our services should have no access to these secrets, and certainly not anything they're not explicitly whitelisted to access. You know, some random server should not have access to the signing keys we use to connect to MasterCard, for instance. Also, very useful to be able to rotate these quickly. There are lots of situations that come up that require you to basically change these in a hurry or even turn them off, like if there's a security incident, for instance. Also, auditing them, very important. So whenever a secret is used, we kind of want a permanent record of that stored somewhere. And also, like I mentioned, we have a security team who would like to understand what secrets we have, which ones are being used, which aren't. And if they're spread around like this, that becomes very difficult. There are technologies that solve this, and basically we use Vault. So we put all of our secrets in Vault, and it's kind of designed to store secrets securely in a way that checks all these boxes. We're kind of in the process of moving all our keys there at the minute, which is a fairly large operation in itself. Vault runs in a high availability setup, so if any one instance of Vault goes down, it's fine, but kind of if all of them go down, that's a bit of a problem in that your Vault is then sealed. There are no instances of it available to serve anything. We do have some ideas about how we might be able to automate the unsealing of this, but at the minute it's kind of a manual operation, and that's in some ways a desirable thing. It requires basically multiple team members to go and unseal the vault. And this ability to seal it is actually very important in itself. Like, if you have a security incident, you can go and just lock down all the secrets. They are encrypted. There is no way they can be decrypted in your infrastructure there, because the decryption key isn't stored permanently in your infrastructure. When a service wants to access a secret, it requests it from a Vault replica, which kind of looks like any other service. And Vault authorizes that access and returns the secret, or returns some operation based on it. And also, very importantly, provides an audit log for every access of that secret. We've had to extend Vault in a couple of ways. One of them is we've added a Cassandra backend for Vault, so we use Cassandra to store basically all of our data. We didn't really want something else that's different. So Vault stores its data in Cassandra. It's encrypted in Cassandra, so Cassandra doesn't have any kind of raw keys in it. The keys themselves are encrypted. And also, one of the things we're looking at the minute is, for a lot of payment networks in particular, some of the encryption they want to use is somewhat exotic. So we're looking at extending Vault to support that. But kind of, again, this is another problem that I feel is reasonably well solved in a traditional architecture, but isn't that well solved in kind of a cloud container architecture. You know, traditionally you would go and buy an HSM and install it. But again, I think this would be a poor fit for us as a software company, and someone that wants to be able to understand how everything in its platform works and have no components of it that we kind of cannot understand ourselves. Or that we can extend it and adapt it to our needs. Like I mentioned with these kind of exotic crypto methods, like some of them might be supported by some HSMs, but that's certainly not the case for all of them. And if we want to add that, that's something we should be able to do. This does bring me on to kind of the last thing, though. And if we go back and look at this diagram again, one of the problems I mentioned is Vault authorizes access to a secret, but how can it do that? How can it assert that the service on the other end of that connection is who it kind of claims to be? This is, again, like, this is something that's solved even if you're running this in a normal cloud environment, but not something that's solved if you're running it in kind of a containerized environment. Because if your services map one-to-one with kind of EC2 nodes, you can authenticate the caller against the EC2 API. That's not the case in like a containerized world, though, because your caller could be anywhere. Like, your EC2 or your sort of node designation doesn't really mean anything. So you need kind of some notion of an identity of a service. And we realized that actually this can be something that solves a lot of problems. Not just this one, but kind of this is where it came from for us. And what I mean by identity is some way to kind of strongly assert to someone else who you are within our platform. And this is something I'm not aware of any open source tool can actually do currently. This is something we're building ourselves. This is something I've heard about existing at a few other places, but never that I've seen implementation of. We had a few requirements for this system that kind of gives credentials to services. We wanted them to be quite sort of tightly scoped. So if one service is compromised and you're able to extract that credential, you shouldn't be able to use it to impersonate another service. So basically it should correspond to one service. And also from the perspective of kind of the service author of the service, this should be very easy to use. We don't want to kind of replicate lots of crypto implementations all over the place, nor do we kind of want this to be something that people avoid using. Ideally, like, this should just be kind of a thing that sits on the file system that you can just go and read. Also, these credentials should be quite quick to validate, which means that kind of, ideally, you wouldn't have to go and make a network call when you receive a network call to say, is this credential valid? And also, like everything else, it should be kind of a highly available system. Like, everything should degrade gracefully when any of it is down. And, you know, the failure of this system for a period of time shouldn't mean that our entire platform is unavailable, because most of our platform, or at least the bits our users care about, will interact with this system at runtime in some way. So this is kind of the architecture we came up with for this. And it's somewhat, again, it's kind of somewhat just extending traditional stuff in a way. Like, these are certificates, the credentials for each service that they receive. and they are issued to them by a certificate authority that's on each node. So on each node, you have a certificate authority that can issue certificates to services running on that node. That certificate authority gets its certificate from a certificate authority that kind of is central for the cluster. And there's some interesting bits to this. For instance, how the service authenticates itself to the node certificate authority. And that actually uses a feature of the Linux kernel, which I've never come across before, but you can, when communicating across a domain socket, authenticate the other end of it and actually assert that it is who it claims to be. There's kind of a lot of obscure features of the kernel like that we've found uses for from time to time. And again, a separate Vault cluster underlies this. So the ultimate kind of root certificate lives in Vault, and that's the one that's used to issue intermediate certificates to the nodes, which then issue server certificates to each service on the cluster. And as I mentioned, kind of this is a highly available system. If the cluster CA were to go down, for instance, the node CAs can continue to issue certificates to services on that machine for a period of time. So the certificates are not particularly long-lived. The ones that are issued to services are only last for a few hours. Those that are issued to nodes last at most for a few days. And I think what we're building does satisfy these requirements. So a node can only issue certificates to services running on it. From a service author's perspective, they are just kind of given a certificate inside the container that's kind of provisioned in there. They are quick to validate. Like, everything is designed so that in this system you can validate a services certificate without making a network call. It has all the information in there. And again, like I mentioned, like, it is highly available in the sense that you can lose components and it won't go away. And you can sort of see how this solves the problem of communicating to our secret store. So when the caller wants to retrieve a secret, it provides its credentials to the store, or it signs the request rather, and provides its certificate to the secret store, and then the secret store can validate who it is. And we think it's useful for kind of a lot of other things as well. Our ledger, which is kind of, I think, one of the deserving of a talk of its own, is something that most services shouldn't be able to modify. They shouldn't be able to insert things into it because it's what kind of controls the truth of the bank, basically. It contains information about who owes us money and who we owe money to, rather, and the kind of transaction history and balance of each account. Also, for building things, again, if you can kind of assert that something trusted has built your container, you can be sure that what's in there is what you want to be in there. Audit logging is another one, in that we would like kind of strong guarantees about what's logged and the durability of those things, and kind of being able to sign them is kind of a basic prerequisite to that. And also the interconnect I talked about, like, that's another place where you need credentials, and this we think can be a good way to provide them. So I've sort of talked at a very high level about 5 things there. I hope people have some questions. And there are lots more things that I haven't talked about that kind of contribute to security in our world. Things like we have a very strong culture of code review, and some things are subject to much more stringent review than others. Other things like no single member of staff has access to production keys. It requires multiple staff to be able to do anything with keys or be able to retrieve a key. And in a similar vein, we're thinking about building systems like multi-party consent systems to do sensitive actions. So when our operations staff even want to do some things like crediting large amounts of money to a customer's account, that should require the consent of multiple people. And audit logging is another one. So, we've built some audit logging systems that I haven't talked about today. So I hope people have some questions, or that's been somewhat interesting. Shameless plug, if these are kind of things you are interested in working on, please come and talk to me. If anyone has any questions, I'd love to answer them.
Hi, sorry, first question. So you run multiple instances of Vault, some for service ID, some for your actual keys of the kingdom.
Yeah.
Can you comment on where Vault for keys of the kingdom runs? Is that running your own colo, or do you trust AWS?
No, that runs in AWS. Actually, our colo facilities have no keys. So they are kind of a dumb pipe, basically, that So they have keys to be able to encrypt connections to the to AWS, but they don't have like keys to the kingdom there.
So in other words, AWS is trusted with the unencrypted content of your vault.
Yes, although the vault is encrypted itself. Right. So like.
Right, but their hypervisor has access to your keys.
Yes, the hypervisor is
acceptable
trusted
for your compliance team.
Yes.
Okay, cool.
Yep. So that was actually like we had to do a lot of work to get our banking license and provide assurance around that.
Hi, thanks for the talk.
Hey.
Really interesting. It sounds like you're running Vault external to Kubernetes, especially the master Vault server that you're using as the CA.
Mm-hmm.
Is that running on CoreOS nodes?
Yes.
How do you manage the fact that those are auto-updating and that seals the Vault?
So they're not auto-updating.
So you disable the security updates
Yes.
in order to, okay.
So actually that currently is the case across our entire platform. So like security updates we apply ourselves regularly, but they don't happen automatically.
Given that you've done this, like disabling the updates, can you talk more about why you chose CoreOS when that's the major selling feature?
So when we chose CoreOS, we did not disable the updates. And I imagine we will re-enable them at some point. The reason we initially disabled them, and it's kind of more of a historic reason, was we had to be on the alpha channel for certain features. And we did not want auto-update on the alpha channel because several auto-updates broke our production system. If that makes sense. So yeah, I would actually really like to re-enable them at some point. I think one of the features of Tectonic would actually be super useful to us in that, though, which allows us to control the updates, which I think vanilla CoreOS has no control over the updates. They're either on or they're off.
Since you mentioned that you have updates disabled, do you mind talking just a little bit about your strategy for implementing security patches, whether they, let's say, if they are critical and those that are not critical? Do you have separate paths for that, or do you just
yeah,
go?
so I think this is actually more than just kind of an OS patching question. It's more of like a change control question in general. And yes, like in the case of emergency changes, as our like change control policy dictates, yes, we can kind of speed things through and do a lot of the process after the fact. So kind of, it applies to basically any change. Like there are kind of normal changes and critical changes and emergency changes. And an update could fall into those categories as well. Does that answer you? Okay, so I guess it's kind of an organizational process. Like doing those things is the responsibility of a team currently, who has the responsibility of kind of looking at what updates need to be made and applying those updates.
Hey, back here.
Hey.
So I guess a lot of us don't have the complexity of like the certificate authorities and Vault
Nope.
and everything that you have in place. Can you talk a little bit about how you rolled that out? Did you take an incremental approach, or was it just like overnight, everything's encrypted, everybody deal with it, let's go?
Specifically about putting keys in Vault.
No, I kind of mean like the whole process. Like, did you just like install Vault and use like some subset of features and not go like as secure? Like we have played with Vault a little bit. You don't have to have like encrypted access to Vault or like use role accounts to access Vault.
Yeah.
Did you like take steps, or did you kind of just go like, you know, all the way?
So we did take steps in kind of. So we did take steps in building it, but in terms of actually deploying this to production, until a lot of those things were there was no sense, for instance. Like one of the things we need to do when moving keys into Vault is rotate them a lot of the time. We don't trust that they are uncompromised. So when we're moving to Vault, we're like, well, this is a good opportunity to roll these keys. With certain partners, that is a very difficult process. So like, no, we haven't gone through that until we're sure that where we're putting them is kind of good enough. But yeah, like everything else, we kind of, we built an MVP of it. We saw that, we built kind of a service interface to it and went from there.
For the connecting payment gateways, you said you installed the secure, the Linux node, right? was there any thought given on how the choice of Linux node, which servers and HA capabilities there, and what was the security policies? Was the network policy applied there too, or was it different later?
So there's a few questions there. In terms of have we given any other talks about this? No. It's actually a very new project in our infrastructure. Like it's only very recently replaced that older system I talked about. So no, there aren't any other talks about it. In terms of how did we choose that approach, it was kind of the only one that made sense to us after banging our heads against the wall of the other approach we went for so long. And the final thing you asked, I think, was...
network policy and how...
Oh yeah, does network policy apply to those? So all the traffic to those data centers has to go through the VPN, basically. Like nothing other than the VPN pods have permission to talk directly to the data centers. So it applies in the sense that kind of egress to those data centers from the cloud is prohibited apart from to there. Or apart from those pods. Anyone else? I think there's someone at the back.
In your kind of cascaded CA mode, what are you doing to assert identity of the node that's getting its signing CA, or is that more of a manual process? So for things like auto-scaling of your nodes.
Yeah. So that involves the EC2 API, basically. Like, is this a node within our infrastructure? Yes or no? Like, is the IP that this connection is coming from that node or not? Like, so it authenticates it like that. And there are a few other checks in there as well, but it's an automated process. There's no like runtime manual intervention needed, apart from to unseal the vault if it becomes sealed. Cool. One more.
Hi. How are the identities of the certificate authorities secured?
I think that's the same question as the previous question.
Oh, I'm sorry.
So the intermediate certificate authorities on each node, or do you mean the root one?
The intermediates.
So when they request a certificate from the central certificate authority, it checks various things. Some of them are kind of checking against the EC2 API, for instance, to see is this a running node that should be able to get a certificate, or does the source IP of the connection correspond to that node?
Thanks.
One behind you, I think.
Sorry, did you say you were using Tectonic for installing your clusters or something else?
We're not using Tectonic at all, no. So so Terraform brings up the Kubernetes infrastructure.
Yeah, okay. Can you tell us anything about how you're managing secrets for the Kubernetes control plane, like CA for the master API, how the nodes talk to, is that also using Vault as a CA?
No, so that stuff is outside Vault at the moment. Maybe that'll change in the future. Those are kind of more static certificates that get provisioned onto those nodes. And this has happened quite recently, if we need to rotate those certificates, that's kind of a process of rotating the entire nodes so they have new certificates on them. Cool, okay. Well, if anyone has anything else, come find me. And thank you.